microlab system with our equipment. We have the microlab sensor adapter module. This can go into any of these three A, B, or C outlets. We'll just plug ours into A. That's ready to go. Then we have our wires. These will be attached to our electrodes. Black on black is what I like to do. The black electrode, which is carbon, will go with the black wiring. So just connect that together. This will go into the current in, or the yellow switch. Okay? Just like that. The red, which will be attached to silver each time, gets attached into blue outlet that says DC voltage out. Now something to know between each trial, you're going to have to take the silver electrode off and clean it with steel wool and or nitric acid. That way you can get off any precipitate. We found that you don't need the nitric acid, but just scrubbing it really well with the steel wool really cleans off the precipitate. So that's how you set up the coulometric portion of actual microlab. Now let's get into the actual setting up microlab on the computer. So now we've got microlab system on, pulling up microlab program on the computer. It's already open, ready to go. So I'm going to click microlab experiment. Then we're going to add sensor. Add sensor, not start button. Add the sensor. So add sensor, we're going to add DC output. Okay? About the fourth one down. Click on it. We're plugged into A, so we click A. You guys have probably used microlab at least enough to know kind of how to add the sensor. So we'll kind of go through this fast. So we've added that sensor. Then we'll also do add sensor, and we're going to add time. Doesn't really matter which sensor you use for time. We'll do ours in seconds. We're also going to add one more sensor for current. That's an A. We're going to be in plus or minus 25 milliamps. Finish. We'll read calibration from file, and now we have to find calibrations. So they are in computer. They're in the local disk. Scroll down on the local disk, and they're in program files, x86. Microlab setup is here. Click that, and click it again. Calibrations, and we're going to use conductivity. Read calibration from file. Oops. Finish. So now we have current, DC output, and time in our sensors. Okay. Again, we've got our sensors hooked up, sensors ready to read on microlab. Now we can actually program the sensors. First thing we're going to do is we're going to show programming buttons. We're going to click on repeat every, it says right now 0.5 seconds. We want to repeat this experiment every 1 second. This is something that you'll also have to do with the pH meter, but we won't show you that because by now you probably know how to set up a pH meter with microlab system. So now it's reading every 1 second. That means that every 1 second we're going to take we should be taking time, DC output, and current should be occurring at that. Okay. Then we're going to click the DAC button. We're going to pull that up so that's reading every 1 second. So it started down here. I just pulled it up here. I can do that again. Pull it down. It's here. Then I'm going to pull it up right under repeat every 1 second. Then I'm going to click on it. I want to set it to 2500 or 2500 millivolts, and that's just set to. And I also want to make sure that it's set to unipolar, not bipolar. Once that's done, click OK, and you have your DAC output ready to go. Having that set, now we can grab current. We're going to put current here on the y-axis, time on the x-axis. You can also drag them to digital display if you want to see them there. Okay, so now that we're done calibrating Microlab systems to run the way we want, both the coulometric and the pH. Mind, we have two separate systems. We have a Microlab set up with only the pH, and a Microlab computer set up only with the coulometric titrations. Microlab, unless you get an extra component, can't run both systems from the same Microlab due to both needing an anchor, an electron anchor point. Anyway, so we've got all of our probes in the beaker now. Now it's just time to add our solvents. So you can see the silver, the carbon, and the pH meter are all in here, and at appropriate levels, we can begin adding our different solvents. So first solvent that I'm going to add in is 0.1 molar sodium bromide. The sodium bromide will react again with the silver ions in solution to form AgBr solid, which is precipitate. We'll see that a little bit later on in the reaction. I'm going to add also about 500 microliters of about 0.1 molar HCl. This, again, will be neutralized by hydroxide made in solution, so that using the pH meter we can see the change in pH and thus an endpoint to the coulometric titration. Last, I'm going to add potassium nitrate to solution, which is just a supporting electrolyte, allows extra ions in solution so that current can flow a little bit easier. Okay, so now that we've got our reactants in, check to make sure all of my electrodes are positioned deep enough into solution to read correctly. Mind, if you change the positions of either carbon electrode or the silver electrode between reactions, that can change the current of the reaction that's passing through. Okay, so all my stuff is in the beaker, ready to go. Both Microlab systems and computers are set up ready to run the reaction. Now it's just time to start it. We found that it's probably better just to have one person start the reaction, because it's a lot easier to fire neurons from one brain than neurons from several, and to time it correctly. So I'll get both cursors on start, and away we go. So now we're about 3 minutes into the reaction. You can see here in the beaker we've got some of the precipitate silver bromide forming on the silver electrode. You can see the difference between the bottom in solution and the top, which is a little shinier, as well as the cloudiness of the solution now. So that's again the precipitate silver bromide. Here you can look at the pH meter. You can see the rise. We're almost to the end point now, but we'll let it level off about pH 9 or 10 before we stop the reaction. Here you can see the coulometric. It's remained about even the whole time, about 20 to 22 milliamps. In the beginning here we had some problems with the silver electrode actually hitting the magnetic stir bar, and so that's what has caused these spikes here in the beginning. So again, you want to make sure that that silver electrode is not too close to the magnetic stir bar. So this reaction for us has been taking about 5 minutes each time. And that's due to several factors. That's due to, one, what current is passing through the system, and that depends on what millivolts you set Microlab to run through the system. and it depends on how far the electrodes are in the solution. It also depends on the concentration of hydrochloric acid or whatever acid you use, the concentration of the acid that's in the solution and is neutralized by the hydroxide. So those three factors, for us, makes the reaction take about 5 minutes. Here we are, pH 10. I'm ready to stop the reaction now. So I'll try to stop both about the same time. Just like I started, one person works best just to click both buttons at once. And bam, reaction stopped and ready to do derivative analysis of both the pH curve and coulometrics. Hey guys, so here we're just going to walk you through the calculations for how to analyze this lab. What we've got up here right now is we've got pH and time. So on the microlab system, you cover the pH, and you have to do pH and time trial on one microlab setup. And this is the data here. So this is kind of what you've done previous already in the lab, doing probably calibrations and other pH stuff in the lab. You take pH and you verse it, or you run it with time, and you get this kind of data. You get a graph here, so this is time on the bottom axis versus pH on the y-axis. So x and y, time, pH. You get that nice, relatively nice slope, about 200. So that's the area we're going to look at for the end point of the coulometric titration. As I take here highlighted now, that's the change in pH, and then I divided the change in pH by the change in time. This gives me my first derivative. Then I do, for the change in I do a second derivative of the change in pH, divide that by the change in time, plot it versus time to get this here. So that's my second derivative of the pH divided by the change in time. And graph that versus time. This gives us the second derivative of pH, and that's what's going to tell us the end point of our calibration. So if I look at this point, I've already put the data here for, I see that the end point end point of the coulometric titration is going to be about 177 seconds. So once we get into coulometric portion of analyzing it, we'll stop analyzing at 177 seconds or thereabouts. Okay guys, so I've just minimized the pH trial now, and I've pulled up what I exported from Microlab. So this is what it's going to come up like when you export it from Microlab if you've exported it correctly. So you'll have current, you'll have time, and you'll have DAC output. Now, this is what you, in Microlab, you set it to 2,500 milliamps, or millivolts is what you set it to originally in Microlab. Now, this isn't important. We don't need to know exactly how much energy we put into the system, but we do need to measure how much energy went through the system still. So we know this because we have current. Current's what matters, the DAC output doesn't matter, so we're just going to delete it. Get rid of that piece of data that we don't need. Okay, for the analyzing, first part we need to do is we need to take the change in time. Okay? So if we have a graph and we have time on the x-axis, current on the y-axis. If we come over here, I'll draw you a quick little graph, little ditty for you to see what I'm doing as we analyze. So, oh gosh, that marker just died. Okay, so here I'm going to have time. Here I'll have currents. So the graph of originally time versus current shows us something like this. if I take the change in time, so the change in time between these 2 points, and then I take the average of the 2 different current values for this, so y1, y2, I take the average of those, it gives me this little square here. That's kind of out of order. But this little square here, this square, if I multiply time versus the change in y, or the change in current, time multiplied by current is in amps per, or volts per second. That will give me the number of volts that have gone through the system. Then I can do some more calculations with volts to calculate how many moles of energy or how many moles of electrons flow through the system. But we'll get to that. Okay guys, so I've made this graph here to show you kind of what I drew on the board. So we're going to again take the change in time, and we're also going to look at the average of the currents. So how do I do this? Well, to start, real quick, I'll do equals time 2 minus time 1. So I'm subtracting the first 2 time slots from each other to get the change in time again. Get that, fill that all the way down. Then I'm going to take the average of my currents. So equals the average of these 2 all the way down. I'm going to fill down all the way. Now, when I multiply, again, the time by current, I'm going to get electricity. I'm going to get volts. This will allow me to calculate electrons later on. So I've got these 2 numbers. Now I just got to multiply them. So equals my change in current times, or my average of current times my change in time. Get that? And fill that all the way down. However, I don't want to go through the whole system like I have in the past. I don't want to take all of these numbers. I only want to go to 177 seconds. Because at 177 seconds, I calculated that in pH to be my endpoint for the titration. So, we'll go down here, we'll find 177. And there, I'm close. So 177 is about this right here. I'll go ahead and leave that one. Well, I'm going to delete this one, but leave the one before it. Even though it's not quite 177, but it's 176.999. Close enough for me. So I'm going to take all the data after this, and I'm going to clear the contents because I don't want that data to be calculated. So if I scroll all the way back up, here again is time multiplied by current. So this tells me volts. So I want the sum of this column equals the sum. Sum of, in parentheses, all these, end parentheses. So I get a sum of this. This is the number of total volts that went through the reaction up into the endpoint of titration, again calculated by pH. I take this number and I divide it. So equals this divided by 1,000. Because right now I'm in millivolts. I want to get it in volts, so I'm dividing it by 1,000. Then I can take that number and divide it by Faraday's constant. Faraday's constant is, I forgot, but I have it written down here. is 96,485. So that tells me the number of electrons that went through the system. So if I know the number of electrons that went through the system, I know the number of hydroxide that was produced, because every one electron that was produced was made from one water. So one hydroxide was made. So this is kind of the end right here. That tells me how many, this cell here. So I'll rewind again. Let me rewind. So this is the sum of my column. This column here is time multiplied, the change in time multiplied by the average of my currents. That is here. That's the sum of all of that. So that's the energy that we put into the system. I divided it by 1,000, so I was no longer in millicoulombs, but coulombs. So dividing the coulombs by Faraday's constant tells me number of moles of electrons in the system. So that's what this lastly highlighted cell is moles of electrons that flowed through the system up into 177 seconds. Thanks. See you guys around. Hey guys, we just wanted to walk you through the electrons again. So we're putting electricity into the system. That's what, again, what the DAC was. We're putting millivolts, milliamps into the system. So we're putting electrons in. Electrons plus water equals half H2 gas and hydroxide in solution. The hydroxide that we produce in solution neutralizes the acid that you use in the solution. So remember, we used about 0.1 molar HCl acid. So the hydroxide that we're producing with the current is neutralizing the acid we put in. That's why we're measuring pH, so we can see the end point of this reaction where there's no more hydronium ions left, and all we have left is OH minus. So this is in supplemental material. I'm sure you guys probably have most of this figured out by now. So thanks for tuning in, and good luck in the lab.